Okay. Okay, hello everyone. Welcome for the second talk of the fall seminar series. This seminar series is done together with the Matrix Consortium. And we have also the ECE students, graduate students who are very eager to see the talk of today. So today we have Ioannis Agadakos. Ioannis has received his PhD in computer science from Stevens Institute of Technology back in 2019. He also have a Bachelor of Engineering and a Master's in ECE from Technical University of Crete. He was a advanced computer scientist at SRI. That's how we worked together. I had the pleasure to work together with him for a few years. And at SRI, he worked extensively in cybersecurity related projects, IoT and deep learning under a lot of different projects sponsored by DHS and other government agencies. He's currently an associate research scientist in Northeastern University. And he's working in software security and neural binary analysis under Professor Robertson. He has published a lot of work in top-tier venues, and he has more than 20 publications in embedded system IoT security and privacy, software security, and deep learning. So welcome, everyone. Ioannis, the stage is yours. Thank you.
Thank you for the introduction, Gabriela.
I will give you the, yes, I realized that the minute we didn't see your slides. Okay. Oh, okay. Now I can, okay, you should have the access now. Excellent.
Can you see the first slide?
Yes, we can. Thank you.
Okay. So first of all, thank you very much for inviting me for this talk. And I would also like to state that since this is a talk that contains a lot of elements from deep learning as well, and this is the first time that I give this talk to an ECE department. And I'm very excited for it because I usually, from the computer science side, I have the opposite questions on relating on the signal processing. So please feel free to ask me anything that you need from the deep learning side or anything that raises a question. And I'm looking forward for your comments as electrical engineers in the end that are bound to be more refreshing than the common computer science side. So, and with that,
Ioannis, a little technical thing. Can you switch the display modes? We can see your presenter mode. Swap displays. Okay. Swap displays, I think, should do it.
Okay, this is good.
Yes, perfect. Thank you.
Great, thank you. So this work with this big title that you see, Deep Complex Networks for Radio Frequency Device Fingerprinting, has been also published under the name that is in quotes, and I would highly urge those that are interested, because it will be impossible to cover everything in this talk, to please refer for more details in the paper. So this work was done under the DARPA FMLS program, the Radio Frequency and Machine Learning Systems. Its broad spectrum was to develop the foundations of using deep neural networks for the purpose of signal processing and radio frequency domain. In particular, this project had 4 main technical areas. We will see the work that I and my colleagues performed on behalf of SRI for the purpose of RF fingerprinting. But what exactly do we mean by RF fingerprinting, and what is the goal of technical area 1? The goal is, put it simply, to be able to collect wireless signals from the air and be able to detect the origin of the device and identify the origin of the device, given a set of devices, to be able to say, okay, out of these 4 or 5 devices, this is the device that emanated, where the signal emanated from. And we wish to be able to do that without being able to identify trivially through a MAC address or any superficial identifier. We assume that we cannot even demodulate the signal. We just want to do that based on the raw RF signal without attempting to do any protocol-specific operations. Furthermore, key design goals of this design area was to be generalizable and protocol-agnostic, given that we do not need any protocol information in doing so. It should be applicable in real environments, and it should be scalable to hundreds, if not thousands, of devices. Okay, but why do we care, and why is that such an important task that DAPA initiated the almost $100 million worth of project in doing so, with so many technical areas? Well, just a few things that this technology is useful and crucial for, especially in the world that we live today, without even going to the military aspects of it, is to be able to do asset verification, meaning that out of a set of devices that have been verified from a company or an authority, that we know that this is the intended device, so there has not been any counterfeit devices on board. Another crucial problem is be able to detect against credential compromise, meaning that assume that you have a particular digital certificate placed on your mobile phone, and that certificate has been stolen through a digital compromise. And then I use my phone in order to digitally sign all communication, basically. If you were able to have a different layer of being able to authenticate, okay, that this is not the intended device, and this certificate should never even be there, then you can detect the credential compromise. And another problem that is very difficult to address and has been seen a lot in practice is what is called relay attacks. The relay attack basically is what you can see in the middle picture. Basically, it's a 2-party attack. Imagine, and it's based on unlocking a proximity-operated door or lock. Imagine that you need to go near a door and you have like a Bluetooth device, and that lock, when it detects that you are there, it opens, right? But this is something that can be spoofed if an attacker has a friend that is near you, even when you are in the university, and they transmit the signal between them, forming a bridge, basically, and that forces the door to unlock. But if you have the technology to be able to say, okay, this transmitter is not the transmitter that was intended, you would be able to detect it. In this particular attack that is very, very sneaky, even if the digital credential is not compromised, it can still be efficient and circumvented, meaning that the digital certificate need not even be compromised in your own device. So hopefully I convince you that this is a very important problem. And as such, it is apparent that such a thing should have been studied from the past. And indeed it has. Dating as early as the 1940s, this problem puzzled a lot of the engineers and scientists of the past, and specifically for the problem of radar fingerprinting. Basically, they were using handcrafted methods. They were trying to identify that a particular radar system is allied and not axis, so they would know which one to attack. But such methods, especially the 1940s method, and others that were developed since, are what we call expert-generated methods, which are very accurate, but they need specific and handcrafted methodologies for each particular protocol. As an extra example, for a much more recent work that was and very, very influential, it's the work of Brick et al., presented at Mobicon, that was able to identify Wi-Fi transmitters based on the tiny errors apparent in each wireless transmission based on the clock. Because as you know, when we have like a constellation and symbols are transmitted, given to the specifications of each protocol, because of the circuity and the clock present in each transmitter, tiny errors that are always rectified from the receiver and discarded can be used and were used in this work to be able to detect that this symbol was slightly misaligned, and they were able to fingerprint and identify the transmitter based on that information. But as it should be apparent from this discussion, such approaches cannot really scale because they have to, you assume specific and accurate knowledge of the protocol, you assume precise knowledge of the frequencies, and they have to be adjusted and verified in each particular setting. However, our recent ubiquitous environment contains a lot of different protocols, different frequencies, and those are just an example set that I'm placing here. But you can think of many others, and there is also the problem of unknown protocols that you have never seen before. The question still remains the same, however. Given that you could collect and detect wireless transmission, even if you see it for the first time, could you answer if you see another transmission in the future that you have seen the originating device before? As it is obvious, for protocol-agnostic methods, the data layer techniques could not be applied, and the expert-generated methods do not scale. The same problem exists with current methods because a lot of them were based on feature detection, which was also generated by an expert. They were either applied in a very limited fashion under lab conditions, and another very important thing is that they were also applied using real-valued networks, and we will see why this is important in the next slide. And allow me to introduce a few. I know that you probably know a lot of radio frequency terminology, but allow me a few slides to introduce some important aspects. So we know that radio frequency signals are electromagnetic signals. We can model them as time series. We also know that they are greatly affected by the channels in the environment, even though they have very smart methodologies in order to address that. And we usually encounter them in two forms, modulated and baseband. This is an example of two different signals that can be encountered in practice, and they were actually part of our dataset. On the left, we can see a Wi-Fi based signal, which has multiple subcarriers, and it's way more complicated than the right-hand signal, which is a simple PAM modulation. Channel effects. In this slide, we can see the spectrogram of the same device and the same signal being transmitted outdoors in 2 different days and indoors. It's the channel effects in the environment can be seen as how they affect each signal in different days. It's quite easier, and the internal signal is quite cleaner than the outdoor captured signal. So, and this brings us to the last slide, which introduces and binds the concept with the complex valued network, and why we believe that it's quite more appropriate to use this. As you know, the quadrature modulators is a revolutionary aspect that appeared in the early 2000s in a mass scale, and it allows you to synthesize any transmitted signal using 2 different orthogonal signals, the in phase and the quadrature phase component. As such, we see that we can express any signal in practice using a complex number composed from the real and the imaginary part. Now, for the artificial intelligence component, a few fundamental components that we need to introduce are the convolutional networks, networks that are extremely good at capturing spatial features, and the recurrent neural networks, which are more appropriate in the RF world. The recurrent neural networks are a special category of neural networks that are extremely good at capturing concept. They have memory, and they can model time series very accurately. And that gives us an insight that there would be an appropriate methodology in order to utilize in the RF spectrum world. A few other critical components. As we know, deep learning networks achieve what we call learning through a process called backpropagation, which is basically a way to bind the output to a given input. A crucial component is nonlinearities that are induced by activation units. You can see an example on the right. Another feature that is also a problem, and we addressed it in the current work, is that they operate on real numbers, and there is no actual support, at least until recently, to encode a complex number in a neural network. And since we are dealing with time series, we need to remember that the recurrent neural networks suffer from a known problem, which is called exploding or diminishing gradients. And the last component of importance is that we require a lot of samples in order to learn something. What gave us a lot of push in this current work was theoretical advances encountered by Travelsi et al. In 2017, which basically they introduced the complex valued deep neural networks. And that gave us the ability to use some components that are accurate and appropriate to operate on complex numbers. For example, recalling that we had the activation units that were based on the real inputs, and that was easy. If a real input is above 0, for example, in the sigmoid, it would turn to 1, or it would be positive, and we would negate all negative values. However, in complex numbers, since we have two different parts, this is not straightforward. So those are two examples of complex valued activation units that they activate in different parts of the complex plane. Another fundamental question that they answered is how do we assign weights to complex valued numbers, or what is the best way to normalize them, which is not straightforward in contrast with real numbers. So, using our knowledge from both RF and the current advances to deep complex neural networks, our approach is to combine all of this and create what we call a radio frequency enabled deep complex network. Our goal is, of course, to utilize this in order to be able to identify those physical characteristics that identify a given transmitter based on raw IQ signals. To put words in a more friendly format, imagine that you have this simple, let's say, power modulation. And imagine that you have a circuitry in the transmitter that produces in one of the devices, in one of the transmitters or the received signals, a tiny artifact in the form of a triangle. Of course, this is an oversimplification, but in order to understand, to get an insight of what we're trying to do. And device 2, its own circuitry, perhaps a capacitor is different, or it has a flow at a given frequency. We see that it has a different pattern composed of a rectangle. So our idea is that deep neural networks, since they are extremely good at capturing patterns and discriminating factors, they would be able to automatically identify these two factors in order to identify device A from device B. As such, we created two different architectures. The top one is a recurrent network, which is based in a long-term in LSTM unit. And the second one is a convolutional neural network. All of them are created from complex valued layers. And there is also a contribution besides the architecture itself. We designed and created an overlayer called the sequencer to facilitate and address the problem of recurrent neural networks of forgetfulness, of exploding gradients and diminishing gradients. As we will see during the results, indeed, the RNNs, the recurrent neural network architecture was significantly better than the convolutional one. And before we proceed, however, let us take a minute to observe two signals. So these two signals are two signals from our dataset, different. The ADSB is basically a signal that is being transmitted from aircraft, and it's meant to replace radar as a means to identify where each aircraft is. It has been designed to be extremely good at overcoming environmental effects. It has a huge range of many miles because of its purpose to be able to be captured from aircraft. And it has a fixed size. It's a very simple signal, and you can see some critical areas of the signals outlined in the axis. And on the other hand, we have the Wi-Fi signal, which instead was designed for mixed usage. You can encounter it also outdoors and indoors, but it's not very good in the outdoors environments. It is greatly affected. And it has a variable length. So those two are some examples of when you claim that you want to do something protocol agnostic. Even for two signals, a lot of parameters might change. In one case, you have a fixed transmission, in the other, a variable one. Also, of critical importance is when you're trying to learn something with DNNs, since they are very good at trying to discriminate and stuff, you should be certain that they don't actually learn something superficial. For example, in this case, you can see that almost half the signal, a third of the signal, in the ADSB case, is composed of a unique 24-bit identifier. So the deep neural networks, if you just provide the signal as it is, it will just learn to, read this number. So it won't learn anything of significance, or it won't go towards the direction of identifying the physical circuitry. Instead, it will just learn how to read this identifier and stop. But this is not something that we want. So, in the purpose of achieving our goals, we had to create several components in order to properly process the signals. But we needed to process them in a way that we do not assume anything for the protocol. So we performed a general data augmentations. One of them was decimation, and we did that because we wanted to estimate, and answer questions. Do we need some sampling, or can we achieve the same effect by using less samples from the collected signals, or we need the entire signal in order to doing so, or we need high rate of sampling. And the sequencer is basically, instead of fitting its sample from the collected signal one by one, it creates an isomorphism containing parts of the signal in such a pattern, in such a sequence, in order to feed them to LSTM as complete steps. So in this case, during the backpropagation step, the backpropagation step will be able to be performed in less steps, because the exploding gradient problem occurs if you have many, many steps. So reducing the number of steps while preserving the coherency of the signal apparently allows us to overcome the problem of vanishing gradients. The last data augmentation technique that is of crucial importance is what we did using signal cropping. Recall that in the picture, we had the signal had the identifier at a given position. But so we wanted to crop the signal in different parts and ask the same question. Given this part of the signal, can you identify the transmitted device? Can you identify the transmitter? Then you crop another part of the signal and you ask, can you identify the given device? That also allows you, if you do it in a completely random way, to be protocol agnostic, because different protocols might have the identifier at different positions. But by cropping the signal randomly and asking this question, identify the device again, then you're forcing the deep neural network to find different discriminating patterns and not the identifiers. This is what this data augmentation technique is attempting to do. It takes the entire sequence of complex numbers, which is basically a signal. It crops it, in this example, 4 ways. It randomly shuffles it and performs classification based on that. Moving towards the results and the data set that we evaluated our approach in. So allow me to spend some time here because I think this is very interesting. So this dataset was created by DARPA, and specifically a subcontractor they had, Crane. It contains more than 60,000 devices and millions, tens of millions, maybe hundreds of millions of collected signals. It's approximately 11 terabytes worth of data. Unfortunately, that dataset is proprietary, although we have been working with them to be able to publish at least a sub part of them. It contains 2 different categories of signals, ADSB and Wi-Fi, which themselves are even more fractured. We have ADSB short and extended, and the Wi-Fi is 2.4 and 5 gigahertz. To evaluate our ability to be protocol agnostic, DARPA withheld a previously unseen signal dataset based on Bluetooth and evaluated our models based on that unseen dataset, which we had never used in training. Another interesting component, and this is a discriminating factor between the current work and other works in the other approaches in the past, is that we have many different receivers. Because an important thing in realistic scenarios is, okay, you classify a given signal in your laboratory given one receiver. But if you don't evaluate how different receivers in practice can affect the signal, then you might have a bias to your given receiver, right? So that's important. Important is also that we have different antenna polarizations to be able to estimate also that it's actually working under different conditions. And we had also devices that were moving. And lastly, a very interesting fact is that in order to achieve our results and the ability to fingerprint the device, a total collection of approximately 53 milliseconds was sufficient in order to perform the fingerprinting. So without delaying, this is an overview of our results, and I will explain what exactly each day means. So in this particular overview, we see 100 devices, and the ADSB signals have 100% accuracy, almost. The Wi-Fi are sufficiently worse, and you can see that so this dataset contains training in 1 day, testing in another day, training in 1 and 2 days, and testing on a 3rd day, and testing indoors and outdoors. And I think that a very interesting part, showing how important your dataset is in training and actually learning what you are supposed to, is if you look at training in 1 day and testing in day 2, which is the second line from the end in the table. You will see that even the best network, the recurrent deep neural network, only achieves a 10% accuracy, right? But if you train on 2 days and test on a 3rd day that you've never seen before, the accuracy almost doubles. And it's actually more than doubles, because in one case we have 50 classes and the other case we have 65 classes. For me, this is very important, it's important because it shows that the channel effects and the environment in reality are crucial. So a lot of published works that just show classification in crystal clear environments without noise, without environmental effects, without having sun or night, or all of these environmental factors that actually affect greatly the signal. I think they're over-reporting, in a sense, the accuracy that these systems can achieve. However, if you have, and from this experiment, I think we can see it quite interestingly, if you have sufficient samples that the network can actually see that there are channel effects apparent, and it tries to see and find more robust features, then you can actually learn what you intended to learn. This experiment shows the effect of preprocessing. As you can see, the ADSB signals are not really greatly affected by preprocessing, which is sort of expected because they are very robust and much simpler signals, and they were supposed to be captured outdoors. On the other hand, Wi-Fi, since it's very accessible on environmental factors, especially when outdoors, it's greatly affected by preprocessing and filtering, leading to better results. This slide actually is interesting because it shows the effect of decimation. It's interesting because even when we were consuming half of the signal, selecting every other provided sample, we were able with almost a third of the parameters to achieve the same accuracy. You can see that the time is not actually reduced because the other parts of the signals, we didn't throw it away. We actually used it as extra samples. So the number of training time remains the same, but the number of parameters is drastically reduced. And that's good because we also have smaller models. Okay, and almost reaching the end. But I kept for last one of, I think, perhaps one of the most interesting experiments, because it shows the problem of learning the wrong thing that I initially specified. Okay, in this experiment, we had 19 classes that are identical transmitters, the same model, the same firmware, transmitting bitwise identical data. And the task for the deep neural network was to be able to identify through the same transmitted data that the transmitter was A, B, C, or D. So as you can see, the initial models, the simple models, ANN is a general linear model, they completely fail when they try to do that. The only model that succeeded is the RDCN, the recurrent neural network, because it's able to understand context. This is our insight in that. And it's also, I would like to note that initially, before we did the cropping, the success in these signals was almost 100% in all networks. And this was apparent under closer investigation. Why? Because during the creation of the dataset, they did a serial way of labeling the data. So they turned on transmitter 1, they collected data, then they switched off transmitter 1, transmitter 2, and so on so forth. And that led the transmitted packets to have different timestamps. So the network learned the timestamps, basically. But when we actually did the proper handling to randomly decide of where to identify the signal, all the simpler network failed to learn the proper signature. And yeah, in conclusion, I would like to say that this was one of the first works at the time that was able to fingerprint devices using raw IQ data and using novel, complex, deep complex networks. It showed that in practice, you can do that in realistic data and not only in sterilized environments. We do not require any protocol-specific information, so we are protocol-agnostic. And it was actually proven in practice when we were evaluated in a never-before-seen protocol, which was Bluetooth. And as you know, Bluetooth is a channel hopping protocol, so it's totally different than the other two. And through our methodology, we demonstrated no-reliance on unique identifiers. Lastly, but not least, since that time, we have received several requests in order to be able to answer new research questions. For example, can you apply the same techniques in passive communication protocols such as RFIDs? Or could you devise a system to be able to fool this detection? Or to be able to do it implicitly through the cell phone? And with that, and I hope I didn't take too much of your time, I would like to take any questions you might have.
Thank you, Ioannis. It's perfect timing. We have time for questions now.
I've got a question, if that's all right.
Of course.
I was wondering if you could speak more to the DARPA data set. Do you know how it was generated? Like, was it done under sort of lab conditions, or were people out there collecting signals without people knowing?
So it was done in several military installations, US bases, which was one of the reasons that we are not allowed to demodulate the data. We are not allowed to read the data. And that's one of the reasons that we cannot publish them, because if someone does, and those are open air captures, there might be classified data there. So there's no guarantee. That is one part. And it was open air. It was captured over 13 days. It has a collection of only indoor data, but in real conditions, meaning that there were multiple devices transmitting. There were also devices transmitting that weren't part of the dataset. And also in the outdoors environment, there were open air capsules, including UAVs and other devices. And if I recall correctly, they used 96 different they used 4 USRPs and 96 different capture devices. For a total of 100 capture devices, 4 of them were USRPs. The other 96, I don't recall right now, but they were very high quality receivers. But I don't recall the model.
We have a few other questions here. What were the challenges to train these neural networks?
That's a very important, very interesting question. It has many answers. So one of the challenges was that this was something that was never seen before. And initially, we were very excited because we saw great results, right? Like when we had 100% accuracy in the 19 device dataset, we said, okay, we solved the problem, but something was wrong. And the thing is that there are so many things, there are things that can go wrong and you won't notice it. For example, those packets had a timestamp there. So when we realized that, so because everything was identical and there was only one part that was a timestamp, and it was very easy for the network to say, okay, you know what, I'm going to take this part and I understand that this is different. So I'm going to classify everything based on that. But basically the network there learned what? It learned that the transmitter 1 was transmitted between 5 p.m. and 5:10 p.m. and the transmitter 2 between 5:11 and 5:20. But this wasn't what you wanted. You wanted to be able to fingerprint the circuitry. And this just learned the superficial thing that was wrong because of the way you collected it, that you just sequentially transmitted the same stuff, but at different time zones. So one of the most difficult parts was to be able to actually learn what you wanted to do. And this is in general difficult in deep neural networks. To give you a better example, more easy to absorb. Imagine that you want to teach a network to learn and discriminate dogs from cats. If you have dogs with a label saying dogs, dog, and the cat, different types of cats, but with a label saying cats, the deep neural network, if these labels exist, it will just learn the labels. It won't try to learn different features. So imagine, so this in a realm that was never before tackled, it was very challenging because we need to spend a lot of time to see what's going on there.
Excellent. Another question. What are the inputs to ANNs and DNNs? If not complex but real, did you use magnitudes or just the real part of the signal?
That also a very nice question. I knew that I'm very glad because I was expecting very different questions from EC. So we actually tried both. Initially, the results that you see in this particular talk revolves in giving vectors of raw IQ samples, meaning it's basically a complex number, 5 and 6J. We actually tried different architectures where we gave magnitude and phase, or we also produced spectrograms of the received signals and we gave images to the networks. But in this particular one that I just showed, you give vectors of captures that are basically a series of I and Q pairs.
Excellent. Another question. Is the noise considered in this work?
Yes, it is. Let me show you, I think in one of the results. Okay, here. We see here that when we say filter and unfilter, we mean giving data without filtering, so with noise, basically. And we see that in Wi-Fi signals, if you don't do filtering, you have much worse results. The ANN fails completely. Right? It's if you see the accuracy, you can't even see it. But the dark blue, that it's almost 1 to 2%, this is the accuracy of the ANN network, which is basically chance die. It learns nothing, absolutely. The other more complicated networks are able to learn, but looking more closely to that, they did what in the process? They did some form of filtering. They learned how to also do some filtering. So yes, it is used. It's very important, and we actually try to do data augmentation, synthesizing new signals by adding custom noise.
Excellent, thank you. You are getting a lot of thank yous here. I don't see more questions. I can ask you a question. So what, oh, no, there is one more. Is the input data sample, 1 second. What is the input data sample that goes into the neural network?
So you mean sample or some, you mean
Luis,
sample?
can you please?
Are you asking the sample rate?
Not sure. Luis, can you please clarify? You can also unmute if you want, or you can just type. Perfect.
Yeah, no, yeah, I guess my question was more on the lines of if it's a digital or analog data when you input it into the neural networks.
Analog data.
You input the, okay.
Yeah, yes, analog.
Okay, thank you.
Yeah, and
sorry.
No, I just wanted to add with this that the sampling rate was 200 megahertz, which is 100 megahertz per channel, ILQ. And this is why a couple of slides earlier that I was talking about the effect of decimation, this is much higher than the Nyquist frequency that you need in order to reconstruct the signal. So we wanted to see, do we actually get any benefit from providing many more samples than needed minimum to reconstruct the signal? And the answer is Nyquist is enough. And
excellent. One more question. Are the multiplication and additions between complex weights and complex features, the traditional complex operations? We might need a few clarifications, maybe.
So
Edmund, do you want to clarify in writing or
Yes.
on voice?
Yes.
Perfect.
What I meant, you know, in each neuron, features are multiplied by weights of that neuron. So, and the output of this neuron would be fed to the activation function. And you showed in one of your slides that complex ReLU activation function takes a complex input and outputs a complex output. So what I meant by my question is when you multiply the features, you're right here. Before that activation function, we should have a linear combination between features and the weights of that neuron. That linear combination is fed to this activation function. So everything is complex here. So I was just wondering, this linear combination is using traditional operations that we all know from high school or early years of college, or is?
yeah, that's a very good question. You can see the math. Usually when I give a talk, I don't want to add too much math because it makes it difficult to explain. But your question is very good. And what happens in the background there, in the complex valued layers, there are many things going on. There is a normalization procedure using the covariance after each layer, for example. So the covariance of the real antivari and imaginary part is evaluated and used in the calculation of producing a mixed information channel. So the transformation used there in the long run is an affine transformation, as you said. And then this nonlinearity attempts to negate one or the other. But it tries to do that in a way that it takes advantage of both inputs. You can see it much better if you check either the work I cite there, Trabelsi et al. Did complex networks. Or if you also read my paper, I also have a discussion there about how to do that.
Thank you. Thank you very much.
Thank you. And let's see if there is any more question. Oh, one more. Oh, why do you think others didn't consider RDCN before for this type of a problem?
Well, it's a combination of things. So until 2017, the paper that I cite there, the complex networks, there were many. So let me answer in a better way. There is actually a paper in 2016 that from OC and Virginia Tech that they were evaluating deep neural networks and how good they are or how prominent they are and how promising they are, sorry, to tackle RF problems, but they were actually thinking and stating in their discussion and future work that it would be great and appropriate to have a complex valued network doing this problem. That was in 2016. In 2017, until then, there weren't enough theoretical components and justifications about how to solve some problems. For example, how do you initialize complex valued weights? How do you normalize complex values? All of these questions were answered in the paper appearing in 2017 in Archive, and later, for the first time, but later published in 2019. So these networks are fairly, very, only recently introduced. So once they were introduced, not only us, other people as well, independently, and that's part of the project, they also evaluated and used these networks. So I think that the reason they didn't do it earlier is because it didn't exist.
Okay, excellent. Thank you so much, Ioannis. I think I don't see any more questions, and I wanted to ask one more question. So what do you think is the biggest challenge when we talk about thousands, millions of devices, when we talk about the large scale of devices?
There are two problems, I think. One of them is that I think that the question of having millions of devices by itself should make us think about how these things can be applied in practice. Like you don't only want to have a closed set of devices, right? You want to be able to do that adaptively. Like I give you a new device, and you should be able to adapt to it. So the open set classification is one question, which also means that there should be limitless, basically, way to identify between devices. And the way I would go in that direction would be in a discriminating factor between using, for example, Siamese network. Is this something that you've seen before or not? Like, and turn it into a binary problem. And the other is that what we encountered in practice when we tried to do 10,000 devices, because that was a dataset that also existed in this challenge, the conventional softmax method numerically wasn't able to challenge that because when you do softmax and you divide everything by a factor and you have 10,000 devices, the factor is so small that it's very difficult. The margin of error is very big. It doesn't give you good results. So over there, I would say that the major problem would be to adapt to hierarchical methods of classification and to use the open set method.
Excellent. Okay, I think I don't see more questions. I would really like to thank you again for your time, and thank you all for joining us today. Have a great weekend, and we'll stay in touch. Oh, one more question, quick one. Which language did you use?
I used PyTorch.
Yeah.
Thanks a lot for inviting me, and it was refreshing to hear questions that are from the other side of the spectrum. Usually I hear only computer science questions, basically, but now I had many questions to the point.
Glad to hear that. Thank you again, Ioannis. Stay in touch. Okay, bye.